Hello viewers and welcome to a new STM32 tutorial video. In this video we will begin to look at I2C or I2C, which is a protocol or bus that is used in embedded electronics to link devices together. So I2C can be used to access external memory and sensor nodes and all kinds of stuff. We will dig into this in some details. I have planned these videos for a while, or at least planned what I wanted to do and how I wanted to explain it. And it has been delayed a bit because it is a slightly complicated topic, but I think I'm ready to dive into it. Let's get the name out of the way first. I think the most popular way is to call it I2C, because if you look at the way it is written, you can see the 2 is actually a square. But I always personally call it I2C, so you will have me saying that throughout this video. I originally planned one video actually to get to this, but it is way too complicated to get this done in one video. And to keep the time of these videos down, my tentative plan, I'm not scripting this, my tentative plan with this is that in this video I'll be talking about the I2C bus and how it is working and the overall principles, and I will be looking at how this is done in STM32. I'll be looking at the HAL library for I2C, and we will probably be ending up scanning the I2C bus, but I don't think we're going to end up actually communicating with the device. My tentative plan is in the next video we will be talking to an I2C peripheral, and in the third video we'll probably be making a library out of it. But let's see how it goes. Now, at the start I have the Wikipedia article of I2C up. So I2C on Wikipedia, and it sort of gives you an overview, quite detailed as Wikipedia does, of I2C. And the important part I have actually taken out of this article, so I'm not going to go through this article, but I suggest you read it. But I have taken the 2 important parts out of this and put it into an article on the STM32 World Wiki. First of all, the I2C bus. Now, the I2C bus consists of 2 signals, a clock signal and a bidirectional data line, and it consists of a master and any number of slaves. Now, this is probably going to upset some of the woke viewers, and I know that if you actually look at Wikipedia, they have changed the terms. I believe they now call it a controller and a target. I call bullshit on that one. It has been around for 40 years or something like that, and they have always been called masters and slaves, and it is actually good terms describing what is going on. The master controls everything on that bus, and the slaves are essentially only there to do as they are told. Now, one of the ways you can have multiple devices on a bidirectional bus, oh, that didn't come out, is by using open drain. That means that the devices on the bus, even the master, is never supplying voltage out on the bus. It is always supplied through some pull-up resistors. Now, the pull-up resistors, you can actually use the internal pull-up in the STM32, but that will be a weak pull-up, since it's only, I think it's about 40 kilo ohms or something like that. Now, on a small device with only 1 or 2 slaves, you can get away with a 10 kilo, otherwise 4.7, or I have even seen 2 kilo pull-up resistors is whatever. I mean, it is fairly flexible, and that is not really relevant for this video, how you actually design it. Now, how does a master communicate with multiple slaves on a single bus? It does that by addressing the slave. So each slave will have a unique address, and the master, before writing to a slave, it will first send the address of the particular slave that is interesting, and then it will either write or read data to or from that slave. Those addresses are 7-bit standard. There is an option these days of using 10-bit, but I'll not be covering that, at least not yet. Mostly because I don't think I have any devices that will actually use 10-bit, so we'll stick with the 10-bit for now. So when a master want to communicate with a slave, it will begin by sending those 7-bit that addresses the particular slave. The following bit is interesting because it indicates whether the slave want to read, the master want to read from the slave, or it want to write to the slave. So all in all, this part is 8-bit. Then there will be an acknowledgement, and these start an acknowledgement and stop states of the communication protocols. They're all handled by the peripheral in the STM32 MCU. So normally you don't have to worry about that. Then you can see that this address and the read-write bit is followed by a message sequence. That message sequence, the format of that is defined by the particular slave. We will look into that later. Typically, a slave will have a bunch of registers that are addressed with another 8-bit value. So typically the first byte will be an address within a particular slave, and then it will be followed by data. For example, right into an 8-bit register, or it could be right into a 16-bit register or whatever. We will look into that later when we're looking at this. Now, for the purpose of these videos, I am going to use a particular device peripheral that I found in my drawer, and that is from a company called DF Robot, and it's called 10DOF, Degrees of Freedom, I assume. And it is a relatively tiny board which contains no less than 4 different I2C devices, all hooked up to the same bus. If we look at the schematic here, we have the I2C interface with the the clock and the data signals, and they are hooked up to 1, 2, 3, 4 different sensor nodes. Now those nodes are an accelerometer, a gyro, a compass, and a pressure sensor. Now, I actually don't know which one is what, but this one is obviously the pressure sensor. So that device is here. Now, in terms of using this device, is an absolutely idiotic device, because typically these sensors have more signals. They will typically have an interrupt line too, so that, for example, the pressure sensor, when the pressure changes, it can set an interrupt so that the master will know, I have a new value for you, so please come and read it. They are not broken out on this board, so the only option in this board is to actually pull the various sensors. But for demonstrating and explaining the I2C bus, this is fine. So if we're actually scanning this device, the I2C bus, when this device is attached, you will get a result like this. You will see the 4 sensors. They will show up on 4 different addresses on this bus, and that's pretty much it. Now, when you want to use an I2C sensor or any I2C slave device, you need to read the datasheet. They operate from the same principles, but they are very, very different when we look at it. So if we look at, for example, the ITG3200 gyro, we can see we have a product specification. Normally that will actually include the register map, but in this one it is broken out in another document. So if we briefly look at the ITG3200 datasheet, you will get a lot of information as usual in these datasheets. Now, datasheets are mostly important for the hardware designers, but as an embedded developer, you need to read these datasheets as well. They are part of the datasheet you can ignore, but overall, these datasheets will have a lot of information that is actually relevant for the developer, the software developer as well. So anyway, that is the datasheet. We will be looking into this in more detail when we get to the development. But let's also briefly look at the register map of this device. So basically, the I2C bus, we have a number of registers internally, and the register map is here. So each register will have an address, and this address will basically, in this case, most all of them are 8-bit. So you can see you have a register here which is called Who Am I, which will return the address that is hooked up to that. Typically many of I2C sensors will have some kind of ID device which can be used in a library to make sure that the right device is actually attached. It can even be used if there's variants of these devices. It can be used in a library to actually adjust. But you can see in this case you have this Who Am I register, and out here it has a temperature sensor and a gyro sensor, and these are read-only registers. So if we read from address 1B, then following 8-bit will give you the high part of the address, and if we read from 1C, we'll get 8-bit, which is the low part of the device. Typically, these devices also have some configuration registers. In this case, we have a power management register here, which will tell us, will configure the device to use a certain clock and whatever. We also have a resolution, a divider, which basically can adjust the resolution of all these. We can configure the interrupt pin, which in our case we can't use because it's not broken out in this this board. But we'll get into this probably in the next video. Now let's look at STM32. As usual, I have created a project which I call I2C1, and as usual I have created our main loop which prints out a tick every second and a loop counter. So let's start enabling some I2C on this. So if we go into STM32 Cube MX, under the connectivity, you can see we have 3 I2C peripherals built into this. I'm going to enable actually the first 2 of them here and here. Now, if we go up to the GPIO and I2C, you can see that there is no pull-up. Now, if I'm uncertain if the device itself have a pull-up, I'll usually enable these pull-up. It is not necessary if there is a physical pull-up on the bus, but the pull-up definitely needs to be there somewhere. So I'm just going to enable those to be absolutely sure that it works. So let's generate our code. And here we got our code. Okay, so as usual, let's have a look at the code, and you can see STM32 CubeMX added an init function for the I2C 1 and an init function for I2C 2. It basically configures a handler like we've seen many times, and then it calls I2C init. Let's have a look at the actual STM32 library for I2C. So we have an I2C HAL module driver, and it's got, as usual, quite a lot of documentation inside. Now, a lot of these functions in this library is related to slave operation and interrupt and DMA and etc, etc. But the important one for us in the beginning is our master transmit. Oh wait, not there. Slave transmit. What is that? Master request, right? Where is that? Oh, they're down here. So there we have our master receive, and master transmit. Those are the two important ones that we will be looking at in the beginning. That will probably, as I mentioned, come in the next video. One we'll be using in this video is the HAL I2C is device ready. So basically you can put a device address and it will return HAL OK or HAL error depending on whether there is a device ready on that particular address. Now the interesting part about that function is that it can be used to scan the I2C bus. If we look at the STM32 wiki, I actually, under STM32 development, I have an article describing, where is it? Here, scan I2C bus. And that one contains a little function that can be used to scan an I2C bus. So let's copy this stuff and put it in our main code. Where are we? We are here. After we print our start, let's do the bus scan. And you will remember in STM32 CubeMX we actually enable both buses. That's because I physically have stuff attached to both buses. So we'll do this scan of one, and then we'll scan one more time on where are we? Okay, we'll do it right. Let me, yeah, C2. I wrote it in capital. So we'll scan both buses. In the first example, we'll scan C1, and down here we will scan bus 2. And if we look at this scan, what it does, it goes through from 0 to 127, which is 7-bit. Remember, the address length is 7. And then we check each device address, whether there's something responding to that address. Notice that we shift the address left by 1 bit. And the reason we does that is because bit number 8, the least significant bit, is actually the read-write bit. So if we take the basic address of an I2C device, we always have to shift that address left before we use it for HAL. It is also described in here. If we look at the documentation in the HAL library, device address target, the device 7-bit address value in datasheet must be shifted to the left before calling the interface. So let's try to see if that builds. And it did. and let's try to run it and see what output we get. There we go. Now I actually have an address, a device attached to I2C 1. I'll get back to that later. No need to dive into that now. But on I2C 2, I have that DOF, 10 DOF device. So we have 1E, 53, 68, and 77, which is exactly what we expected from this device. So we essentially have 4 different I2C devices here. If I want to communicate with the gyro, I have to use 68 as an address in hexadecimal 68. And if I want to communicate with the pressure sensor, I'll use 77 as the device address. So that's pretty much all I plan to do in this video. In the next video, I will pick one of these and I'll look more into that and what it can do. I'm not sure whether I'm going to use the pressure sensor or the gyro yet, but have a look at what they actually do. But I'll probably use one of these. They are the least complicated of them. The compass, I'm in the middle of a concrete reinforced building, so I'm not sure that will work overly, and it's hard to demonstrate. So I'll probably pick one of these and use them in the next video. As usual, please like and subscribe, and I love comments. One of the things I'm struggling with, as you know, this is I'm still learning to do these videos, and I'm struggling to find the optimal length of the videos. Should I make them long and detailed, or should I make them short and sweet? I don't know. I personally think that half an hour is too long, which is why I decided to break this into 2 or 3 different videos, because otherwise it would be 45 minutes and I doubt there will be any viewers left at the end. So please let me know what you think is the optimal length of these videos, or any other comments that you might have. As usual, the starting point, what I have so far, will be committed into our GitHub repository, which you can see linked in the description page. That's all I plan for now. As usual, have a wonderful rest of the day, and please enjoy. Bye bye.